Okay, so here's our last 5 examples. Let's have a look through these ones. This first one, the integral of x to the 5th e to the negative x cubed dx. Again, if you haven't done so already, pause the video and work through these ones. Figure out which one you're still having troubles with or you'd like to see get done, and then you can navigate to that portion of the video. So what can we do here? Well, ideally I'd like to make a substitution because I see that x cubed in the exponent. If I could substitute for that and just make it a u, I'd be happy. So I substitute for the x cubed. I'm going to need to use up an x squared in the substitution, and what's left here is going to be an x cubed. Oh, but that's fine because I can rewrite an x cubed in terms of u. So it looks like substitution will work. Let's see the details. Substitute u is equal to negative x cubed. du is equal to negative 3x squared dx. When we do this, I'm going to split up that x to the 5th into an x cubed, x squared e to the negative x cubed dx. The reason I've done this is because I need an x squared dx to appear. That's this one here. I need an x cubed to appear. That's that one. But also that one I can replace with u. So that's our goal, is to make these replacements. That first x cubed I can rewrite as negative u. The next x squared dx can be replaced with negative 1/3 du. So notice that negative sign's gone now because I got to cancel it with the one that was coming from the du expression. And then I got an e to the negative x cubed, so that's u du. So we've done a substitution. We reduced it down to this. At this stage, through experience, you do enough of these things in the by parts sections, you realize that this was one of those examples we did in by parts a couple of times. And so at this stage we can say, oh, okay, I need to use by parts to finish it off. So one thing here for by parts, if you're used to using u dv, you might run into a bit of confusion because I've already got u as a variable. There's a quick fix for that for this substitution. It's often called a w substitution. People use w instead of u for substitution. So I could change all of those u's to w's. And that way now I'm free to use the letter u again in the by parts method. So u is equal to w, dv is equal to e to the w dw, du is equal to dw, v is equal to e to the w. Now that's going to be, using by parts, 1/3 of w e to the w minus 1/3 the integral of v du, which is just e to the w dw. So I've reduced my original integral through a substitution to one involving w e to the w. Through by parts, I've reduced that to an integral involving just e to the w. So now I can anti-differentiate that piece, and I just get an e to the w. Now I can put everything back in terms of the original variable x. So this is 1/3, w is negative x cubed, e to the negative x cubed, minus 1/3 e to the negative x cubed. Or in other words, negative 1/3 e to the negative x cubed plus 1. And there's our result. Oh, should add a plus c once we've gotten rid of the antiderivatives there. Or once I got rid of the integral sign. Then we've got our general antiderivative with the plus c. And so there's our result. How about the next example? Let's see, b is the integral from 1 to 5 square root of negative x squared plus 6x minus 5 dx. Now what can we do with this? Well, it looks like the square root of a quadratic. If I complete the square of the quadratic, I could write what's under the square root sign as something squared plus a constant, so like maybe like a u squared plus a, and then maybe I could use trig substitution like sine. So that's my hope, is maybe complete the square of what's under the root sign. So let's note that negative x squared plus 6x minus 5, I want to be able to write that as x something squared plus a constant. So if I'm going to write x plus something squared, I need that number so that when it doubles gives me 6. So I need that to be a 3. So now let's see, what does this first part give me? It gives me an x squared, negative x squared. It gives me a 3x plus another 3x, it's a 6x. Oh, but there's a negative sign out front. That's going to make it negative 6, so I'll make that a negative in there so that it becomes a plus 6. So in other words, just expand that out and see that you get the first two terms. The last term I get is going to be a negative 3 times negative 3, that's 9. Negative 9, because of that negative sign there. I want it to be negative 5, so I add a plus 4 on the end. So I've completed the square now. So note, we've just completed the square. So the integral becomes 4 minus, I'm just going to write it in the opposite order, dx. Okay, now what can I do? Well, I could substitute u is equal to x minus 3. So du is dx. Our new limits of integration, what are those going to be? Well, x is 5 implies u is 2. And when x is 1, that means u is negative 2. So our new integral becomes the integral from negative 2 to 2 of 4 minus u squared du. Okay, so now what can we do? Well, this looks like a good candidate for doing a trig substitution. U is equal to 2 sine theta, because then I could get 4 minus 4 sine squared theta, rewrite that in terms of a cosine. But let's just pause for a second. I don't think we need to do that. Because what does this graph look like? Well, square root of 4 minus u squared, that's an upper semicircle of radius 2. And we're trying to integrate that thing from negative 2 to 2. So all we're doing is trying to find the area of this region. That's what that integral represents. So it's the area of half a circle of radius 2. So that's 1/2 the area of a circle of radius 2, pi times 2 squared. Or in other words, the result is 2 pi. And so we're done. How about the next example? The integral of square root of 1 plus x, square root of 1 minus x dx. What can we do with this? Well, one thing, when I stare at this, one thing that pops into my mind is they are closely related, 1 plus x, 1 minus x. I'd like to get rid of the square root, at least one of them. I can get rid of the one on top by multiplying top and bottom by a 1 plus root, square root of 1 plus x. So I'm just going to multiply by 1 in a fancy way. This thing here is just equal to 1, so I'm multiplying by 1 in a fancy way. So this becomes then the integral of 1 plus x, and the denominator becomes the square root of 1 minus x times the square root of 1 plus x, so that's the square root of 1 minus x times 1 plus x, or 1 minus x squared dx. And that can split up into 1 over root 1 minus x squared dx, and a plus x over square root of 1 minus x squared dx. And that looks like I've made some progress, because here that looks like what we're going to get is an arc sine. But what about here? Well, this would be a substitution. Something like u is equal to 1 minus x squared. And I'll leave it here for you to finish the details off. The point is that we've made some progress, and now we got to two integrals that we know how to deal with. The second one being just a straight substitution. Let's look at the next example. The integral of cos x over 4 minus sine squared x dx. Well, there's an obvious choice that should be screaming at you right now. When you see a cosine sitting by itself with a sine involved in the expression, you can see, well, cosine is the derivative of sine. So we can immediately dispense with those things by making a substitution. U equals sine of x, du is equal to cos of x dx. And so that becomes the cos x dx joins together to give me a du, so I get a 1 over 4 minus u squared du. Now at this stage, we've reduced it down to a rational function. The denominator factors. So this looks like a perfect opportunity to use partial fraction decomposition. We've got that it factors into a 2 minus u and a 2 plus u. So we want to write it down in the form of the integral of something over 2 minus u plus something over 2 plus u. And the question is, what should our numerators be? We could use arbitrary variables for those and then set up the equations to solve for them. Or we could try to engineer them. We need them to be, we need the result to be 1, so I need this times this and this times this to add up to give me 1. I don't want the u's to survive, so whatever I put up here, I've got to put the same number over here, because a u times that number on the top of the first term will be equal to negative u times the number on top of the second term, because they need to cancel out to leave no u's in the numerator. And I need to make sure that the 2's cancel out, so it looks like a quarter is going to work in this case. If I do the cross multiplication, so I get 1/4 times 2, that's a half plus a quarter u, and then the other side is a half minus a quarter u, so a half plus a half is 1, and a quarter u minus a quarter u goes away, so I can get those values there. Again, if you want to use the method of just putting arbitrary constants up there and working through the process, go for it. Perfectly valid way to do it. Sometimes you might be able to eyeball these things though as well. Now we can take the antiderivative, so that's going to be a quarter ln of 2 minus u, negative, because of the fact that there was a negative there. And that's a plus 1/4 ln of 2 plus u plus c. And now we can put everything back in terms of our variable x. 2 minus sine x plus 1/4 ln of 2 plus sine x plus c. And so there's our result. Okay, this brings us to our last example. That is the one that involves a hint as well. 1 over the square root of 1 plus x squared dx. And the hint says use the substitution x is tan theta. So let's see what happens. X is tan theta. So dx is derivative of tan is secant squared theta d theta. So we make that substitution. Why have we used this substitution? Well, 1 plus tan squared is secant squared. Square root of secant squared is secant. So the denominator becomes a secant. The dx becomes a secant squared theta d theta. And so there is our new integrand. We can simplify it a little bit. That's the integral of secant theta d theta. Now at this point, either you remember the antiderivative of secant theta, or you remember how to derive it. And in this case, I'll just refresh our memories how to derive it. So what we're going to do is we're going to say, well, I'm going to multiply by 1 in a fancy way, secant theta plus tan theta over secant theta plus tan theta. So that's 1, a fancy way to write 1. Why have we done that? Well, when I expand it out, I get a secant squared theta plus a secant theta tan theta. And what's on the bottom is secant theta plus tan theta. Now, if you look closely, the thing on the bottom, its derivative is exactly what's sitting on top. Derivative of secant, that's secant tangent. Derivative of tangent, that's secant squared. So the derivative of the thing on the bottom is exactly what's on top. So that means that the antiderivative of this thing is the logarithm of the thing on the bottom. Okay, I suppressed a substitution, but really there was a few steps in here. The very first being another substitution here saying, let's say W is equal to secant theta plus tan theta. So we make that substitution. That reduces it to an integral of 1 over W. You anti-differentiate, that's ln of W, and then you put everything back in, and that's ln of the absolute value of secant theta plus tan theta. And so there is our result. And as a last step now, we've got to take our final result and re-express it in terms of the variable x. Now, in order to get back x from theta, we have to go back to our original substitution. So x is tan theta. What's often helpful here is to draw a right triangle that gives the relationship between x and theta. So if our angle is theta, tan of theta is opposite over adjacent, the length of the side opposite over the length of the side adjacent. And that's supposed to be x. So I can make that equal to x and that equal to 1. And now, using the Pythagorean theorem, I can get that the hypotenuse length is 1 squared plus x squared, square rooted. So in other words, I can write it as the square root of x squared plus 1. Now this gives us our relationship between x and theta, and we can get relationships between the trig functions of theta in relation to x. So for example, we're interested in secant of theta. Well, what is secant of theta? Well, that's 1 over cosine. Cosine is adjacent over hypotenuse. So secant of theta would be opposite over side adjacent, which is 1. So secant of theta is just the square root of x squared plus 1. So we can rewrite this as ln of the square root of x squared plus 1 plus tan of theta, which is just x plus c. And so there is our antiderivative expressed in terms of the variable x. All right. So we just went through a bunch of examples of how to compute antiderivatives using all the techniques that we've learned so far in this course. And the idea was to just get some fluency and to see how these different techniques can be applied. And notice the key ingredients were always, you need to be able to do those antiderivatives of those basic functions quickly, because you need to know if the steps you've made get you to something that's more easy to deal with. All right, so thanks very much for watching, and we'll see you again next time.